Yeah. Good evening, everybody. Welcome to the very first day of our SSERD Outreach Program. This is Rajeeth here, and today we are going to start our journey to explore the space and the outer mysterious world. Joining with me will be Vishesh, and we are just good to go.
A very warm welcome to all the Earthlings assembled here. I am Vishesh, one of the two sailors on your astro voyage. Rajeeth, how did your interest in astronomy and astrophysics begin?
Well, since I was a childhood, I used to look up at the sky and observe the stars and other moving objects in the night sky. I wonder few stars would sometimes twinkle and few didn't. I wonder what are those things which are not twinkling. Well, later on I came to know that these are the planets. Actually, stars twinkle and the planets don't twinkle at all. And that's how my enthusiastic about to know how the universe actually work. Day by day, just moving on, I came to know about more and more details of the space and time, and astronomy was a subject which fascinated me because this is not something which just originated in the modern history. It has a vast history beyond, and many people are crazily observing and discovering beautiful and mysterious things out in the universe. So today in this class, we're gonna learn what astronomy and astrophysics actually mean. What are these two crazy words? Well, I'm supposed to say that this is something which were originated by the Greeks, and the Greeks were the one to represent the astronomy and astrophysics in their own observations through their own observations, and that's how it all started. So let me start with today's presentations, and we are going to take up this journey, explore the space. Today we'll be learning about planets, stars, uh, our own Milky Way galaxy, ancient astronomy, the sculptures presented by them, dark matter, dark energy, and the expansion of the universe itself. Well, first, let's just put a few questions within ourselves. What astronomy actually mean? What does the sky looks like when we observe from various aspects? Sometimes the stars are visible bright enough, but sometimes they are not at all. But today we're going to end up answering all these questions beautifully. So before beginning our lecture, we just look into it. The quotes which were delivered by the famous physicist Richard Feynman. He said that it doesn't matter how beautiful your theory is, or it doesn't matter how smart you are. If it doesn't agree with experiments, what all the observations you do in the field of science and technology, it should be evidented. It should calculate. It should be calculated, and it should follow some kind of evidences, some proofs that should be needed. And that's how it's all began. Well, the second quote itself represents the first principle is that you must never fool yourself, and you are the easiest person to fool. Well, this has a very great meaning within itself. You know why? Because the person who is confident about his work, about his curriculums, is the guy who is going to change the world with many outstanding discoveries. Just moving on, we will look at what actually the ancient Greeks did, because they were the one who started defining astronomy. They started the concept of defining astronomy, and that's how it's originated. Whatever the people used to observe in the sky, in the night sky, they used to either create it in the form of sculptures or the drawings. Well, today we are curious to know what everything means. Science is something which begins with curiosity and imaginations, and you have to have a strong, valid evidences to just prove your observations and move forward. Starting today, Greeks, whatever they present in the form of sculptures, as I mentioned. So one of the sculpture is very famously represented in the England, which is situated in England, called the Stone Age. These actually represent the sunrise and sunset of sunrise and sunset at different weathers, at different seasons. Sometimes in winters, sometimes in summer. Is like a clock. It moves. This is operated as a clock for the Greeks. And not only the Stone Age, there is another one called the Chinchiliza, situated in Mexico. Well, this was the ancient observatory. You guys, can you imagine? It was constructed in 1880. Look at the time when it is. People used to like create astronomy, but that time we didn't have telescopes. We used to just look up through naked eyes, and even the naked eyes needed some height to just get a clear vision of the universe. Well, this doesn't mean that these two things are just kind of observatories, this kind of representation. But what is the mechanism they used to understand the planets, to understand the stars, to understand other different celestial bodies? Well, we have the machine, an anti-crack machine, which was developed by the Greeks itself in the 1900s. It represents the motion of each and every individual planet. People used to calculate the elliptics happening of eclipses, happening of eclipses, the zodiacs, the constellations, everything were manipulated with this clock itself, and it consists of total 72 gears, where each and every gear represented each and every planetary motion. It could be ours, Earth, Mars, Venus, etc. But you might be wondering, like, these were just the sculptures or the mechanical instruments. But before that, when all this began, how ancient Greeks used to represent their observations? Well, it was through paintings, through drawings. Drawings is something which was came way across in the ancient periods. In this drawing, you can just see two objects. Can you guess what it is? It's Saturn and the Moon. See, today we have telescopes and we can just directly look up in the night sky and observe how Saturn actually looked like. But at that time, people didn't know how to show it. That's how they used to draw. And whatever they observed, they used to draw in a systematic way. And that's how the Saturn painting represent at what different angles, at what different directions people actually observed it. The second one comes with the phases of the moon, where you can see a little bit is little dark and the other side is little bright, which represents the phases. You know what is full moon and what is a new moon, and that's how. And sometimes you can even see the moon is partially visible, not completely, and that's how it is represented. Over here, the dark portion is the one which is not visible to us, and the bright one, or the light one, is something which is visible to the Greeks, and that's how they have represented in the form of drawings. Now you might be, I'm just saying Greeks, right? Who are these Greeks actually? One is the famous Aristotle. He came up. He was a man who actually started looking up to the sky and making his theories which relates to the planet, our own solar system. One of his famous model called the geocentric model was proposed by him in which represents the Earth as a center. Those in the modern days, people used to believe in God a lot, and they imagined that Earth is a creation of God itself, and we are the center of the universe, and all the other planets and even the sun itself revolve around the Earth. But this was little wrong. It was not a correct observation, and few people were also trying to counterpart it, and that's when came the Copernicus. He came up with his own model called the heliocentric model. He represented the sun as the center of the universe, and the Earth, planets, and all other different objects revolving around the center sun. And this was quite acceptable. And today, whatever we know is the Copernicus revolution. Whatever we use is the Copernicus model itself. Just a short representation of geocentric and heliocentric model. In the first image, you can see the geocentric model, Earth as center. And the second image, you can see the heliocentric model, the sun as a center. And that's how it all began with the Greeks. Time went on, more and more discoveries were done, and today we are in the modern astronomical world. But there was one point which was missing, and that was the mathematical proof. As we mentioned in the beginning of the class itself, we need evidences to prove whatever we observe. That's how the famous mathematician Kepler, Johannes Kepler, he was the greatest mathematician of his kind. And he came up with Kepler's law, which represented the planetary motions of all the planets around the solar system. And it was not only applicable in our solar system, but it was also applicable for all other solar systems which were present in the universe. Kepler's first law represents the planetary motion, where the sun and the earth or any other planet is represented as the two foci of an ellipse. Now you might be wondering, what is this ellipse? Well, if you just take a circle and stretch it along one particular axis, that becomes an ellipse. It's quite simple. You can also mention like oval. The second law represents the area, the distance covered by the planet in one particular direction is same as that of covered in the other direction. In this figure, you can see the blue region, two sides. The first region is little narrow, whereas the other one is little thicker. But the time taken to cover those both distance is equal, and that is mathematically given in Kepler's third law, where time is proportional to r cubed, where t represents the time factor and r represents the distance factor. But Kepler was not only the one guy, there was someone else too, Galileo Galilei. He was the guy who actually started using telescopes, and there was the modern astronomy began. Now you might be wondering, what is this telescope? How did it work? Well, you are going to come to know about it in very short time.
Thank you, Rajeeth. You did mention that Galileo was the first one to use the telescope for space observations. But currently, are any of our telescopes much better than them in advancements? Yes. And there are good number of types of telescopes also. First and the basic one is refracting telescopes that used refraction or the bending of light as a principle. But this didn't last for quite long because the mirror used was quite heavy and also visible light got split up into its various wavelengths, thereby not allowing for proper observations. Enter deflecting telescopes, which did not use lenses but used mirrors. These allowed the telescopes to be much smaller in size and cheaper in manufacturing. Here you see the path of light that is taken inside a telescope. But though we have advancements in technology of telescopes, there's always some hindrance that has to come in our way. And here is our own issues. We put up lights, artificial lights everywhere for our convenience, but it hinders the astronomical observations. Then we have Earth itself playing a role. When we observe the universe, we require to see all the wavelengths, but only the visible light is allowed to transfer to the grounds, whereas X-ray and gamma are blocked by the atmosphere. Again, atmosphere playing a spoil sport. Turbulence happens when there's a medium in between the telescope and space. So here being the molecules in the atmosphere. So what do? Take a whole experiment up in space. So here we have a space telescope, Hubble, which has taken the image that you see on the right, and you could observe the good amount of difference in both the clarity of both the images. So we have come up with a good number of solutions. Is there nothing else we can do? Yes, we can advance our telescopes by using adaptive optics, which reduce the distortions that the light produces on a telescope, thereby increasing its efficiency and its image quality. But we do want to observe a lot more in the universe with much more clarity. And we cannot have a telescope that is as big as Earth. What do? We combine all the little telescopes or the arrays that are available into one single big telescope that could have the size of Earth, virtually though. And this principle is called interferometry. Here you see interferometer that is based on the radio waves. And here you see the interferometer, the device used for observing the optical wavelengths. We spoke about seeing, but what do we see and how do we see? We see in different electromagnetic spectrums, meaning the whole wavelength of EM waves is divided into many categories. We have gamma and X-ray, and we have satellites working for each of these particularly, which give us a vast and a wide range of observational capabilities. I did say electromagnetic radiation has many ranges. So you can see how the radio waves and the gamma rays difference. The wavelength also changes, energy also changes. And okay, we did receive an image, but now how do we process that image that is taken by a telescope? Enter charge coupled device, which converts the light that has entered into electrical signals and then into digital images that are very well observable by us, thereby making space observation very easy.
Well, you might be wondering, till now you have just seen how Greeks actually work, how they work on the night sky, and you have also observed the telescopes. You have just came to know about it. But you might be still wondering how Greeks actually managed to just look up at the sky and work on their own work, own progresses. uh, they actually discovered patterns in the sky, and that's today we know those patterns as the form of constellations. There are total 88 constellations in our solar systems, where and in these 88 constellations, 12 are the zodiac signs. You might be now wondering what is the difference between the zodiac and the constellation. Well, zodiacs are the part of the 88 constellations, and but the zodiac is something where our sun lies in a particular constellation. We have 12 constellations which are named after the 12 months, and that doesn't mean that these other constellations are not in the use, but that's not clear at all. Other constellations are work as a map, as a clock, and sometimes as a season indicator. People, Greeks used to observe the night sky and used to grow their own crops. They used to travel from one place to another just by mapping out the constellations itself. And today, these constellations also affect us by looking up the sky, and even helps the people who travel in the sea sometimes. Just we have looked at how the constellation and what the zodiac actually means. This is where the sun actually lies, and that's why they are called zodiacs. But even moon has zodiacs. 12 zodiacs equals the 12 months and 1 year. But what that actually 1 month is represented, that it is represented in the format of the phases of moon. Sometimes we see a full moon, sometimes we see a new moon where there is no moon itself, and frequently you see the partial moon. But the time period which is taken for one moon to just travel along its whole phases and once again form a full moon, it's the one particular month, and it's around 29.3 days. Moon travels in an orbit around the Earth, and sometimes there is a chance that moon, sun, and Earth appear in a one single line, and that's how the eclipse are formed. The lunar eclipse is when the Earth comes in between the sun and the moon, and the solar eclipse is what when the moon comes in between Earth and the sun. Lunar eclipse happens almost frequently, but solar eclipse occurs hardly 2 to 3 times a year, which is really rare to observe. Now, just looking after the eclipse, you will learn about our planets itself. So just stay tuned.
We did observe how the moon and its positions affect us. But do planets also move and do their positions matter? Yes. A heads up. Inferior planets are those that are between Earth and Sun. For example, Mercury and Venus. Whereas the superior planets are those that are beyond Earth, Mars and above. So, conjunction is a phenomenon happening when the Sun and Earth form in the same line. An inferior conjunction happens when an inferior planet comes in its way. whereas a superior conjunction happens when the sun itself comes in between. There is another phenomena called as elongation. Rajit did mention that our orbits are elliptic, meaning that during the part of the year we sometimes are close, whereas far to the sun. Aphelion is the farthest point from the sun, whereas perihelion is when the planet is closest to the sun. And opposition is when Earth is sandwiched between sun and a superior planet. So we did see how they move, but did we see how they form? Now we see. A star is formed from a planetary nebula, where a planet also is formed in its neighborhood. A planet also includes all the planetary dust that the sun or any other star produces nearby and thus forms along with the tiny moons. So we did see a planet being formed, but after it is formed, what does it have in? The inferior planets, along with Earth and Mars, have a rocky surface, whereas the planets beyond Earth, or beyond Mars, sorry, have a gaseous environment. Totally, those are called as gas giants. So Jupiter to Neptune are all gas giants because they are mostly made up of hydrogen, methane, carbon dioxide, and so on. Okay, we did see planets forming, and then we saw what they are made up of. But how long do they take? The time phenomenon. Here we come. Here are the days that each planet takes for a single day of its own, though measured in Earth days. And also, you see the inclination of planets that they have with a perpendicular axis from the sun. Are there anyone else except for planets in our solar system? Yes, the unfortunate dwarf planets. These sadly do not make up or do not classify for the planet status, but they do exist. And our solar system has Ceres, Pluto, sadly, and Eris. So, is there something outside our world? And the answer turns out to be yes.
You have just seen the planets of our solar system, but our sun is not only the one star among in our own galaxy. There are trillions and trillions of other stars too. And you might be wondering, like, how our star has a solar system. Other stars might not also have. Yes, actually they have, and there those planets are called the exoplanets. Well, exoplanets are usually discovered for the other stars in other galaxies. It could be from other galaxies or the stars from our galaxy itself. But these planets are not at all observable from our Earth. But there are techniques to observe and to understand how these exoplanets actually work or look. We use three simple techniques called the Doppler effect, transit effect, and the direct imaging. Direct imaging has a huge drawback because just looking up to the exoplanet, looking up to the star and taking a picture sometimes lead to the blurriness of the planet. The luminosity of that star is so bright that the planet just gets covered into its shadows, and this leads to an not clear understanding about the planets itself. For an example, I will just show you an image which is was taken by the Hubble. It showed that one particular picture you can observe that planet is not at all visible in the optical wavelength, but when it comes to the infrared wavelength, you can see a tiny spot, and that's how it's all built. That's how it's all understood. Now coming up next is the Doppler effect. Doppler detection is something represents the distance from where the planet is situated, how much distance the planet is situated from the star, and its motion, or we can call this speed. Well, this is understood by collecting the spectrum or the wavelength, by observing the wavelength. When the planet moves away from our observatory, we get a red shift or a red color wavelength where the wavelength is long. But when it gets closer to the telescope or the observatory, the wavelength compresses and undergoes blue shift, and that's how we understand the motion of the planet, the speed, its size, its distance from the star. But this is not the end. We also need what is the planet made of. Just a short representation of how Doppler effect also have a drawback. We can't observe Doppler effect when the inclination of that solar system is actually at 0 degrees. 0 degrees in the sense the star and the planet are observed in a circular orbit. It's not that clear because the wavelength is uniform in all directions, from all parts. But it could be observed when it comes to an inclination of 90 degrees. That's how the planet just crosses away the star, and the detection of waves could be collected very easily. But even we have to understand what is the nature, what is the temperature, what is the atmosphere of that planet. Well, that's how when it comes that's how when it comes to the ecliptic, when we uh, also called as the transit method. Transit method is somewhat described in graphically, because in the transit method, the luminosity changes. The luminosity of that star changes. When the planet just crosses the star, does not allow one particular amount of light to get to us. Just and that light, through that the curvature of that graph is through that we can calculate the atmosphere, the temperature of that particular planet. But you might still wondering that how just a planet could be observed, how could be manipulated. These three methods actually play a dominant role. Well, just don't be panic if you couldn't see the PPT. Don't worry, we are just here to explain it. Okay, you have just looked into the planets, our solar system, other solar system. Just just we'll look up to the galaxy part, because galaxies is something is really important. These are all stars. These all everything is situated in our own Milky Way galaxy, and there are millions and millions of other galaxies too in our own in our own universe. Just just take a look in of our own Milky Way galaxy. Our Milky Way galaxy has various parts. The we have the other very different planets orbiting around many different stars. Just before to the galaxy part of view, I would like to show a video where you can see the detection of exoplanets being taken up. The exoplanets were not only they are not observable from the ground. They need to be observed from space, and the space probe which is looking at it is the Kepler space probe. Now you might be wondering what exactly the Kepler space probe looks to the galaxies or looks to the universe. This is something it actually looks. You can see this is there are n number of solar systems, or you can say the miniature size of the solar system being observed by the Kepler probe. Because the transit, whatever it happens, the Doppler effect, whatever it takes place, that couldn't be done in one particular planet for one particular solar system. And that's like if you're performing the transit to one particular solar system, the other might undergo Doppler, and vice versa. This could create some kind of disturbances in the understanding. So that's why millions and millions of solar systems are observed at a one go. And according to NASA, we have according to NASA, till the year 2013, the Kepler has discovered around 2,740 exoplanets. Can you imagine the number? These many exoplanets are there, which is few are similar to Jupiter size, few are Neptune size, and few are Earth size. The blue dots which you can see in the graph are the Jupiter sized planets. And the red dots you can see are the Neptune sized planets. The yellow dot which you can see are the Earth sized planets. Due to the increase in the technology, slowly, the Earth-like planets discovery are made. Well, we have seen the planets, we have seen our moon, we have seen the eclipses. But what about our own parent sun, parent star, the sun? You will be asking,
But how do these stars form? They form from the planetary nebula, the cosmic dust that is available everywhere in the universe. So, if the dust is available, how is a star getting clumped together to have that much of energy? Answer: gravity. Each molecule pulls each other and they compress each other due to gravity to such an extent that the temperature rises so high and nuclear fusion begins. Nuclear fusion is a combination or the fusion of elements, hydrogen or hydrogen to form helium, and then went go on and on and on. But as this goes on, do you think the star will achieve a stable state? Yes, the outward force of nuclear fusion is balanced by the inward force of gravity, and so we have a stable star. And this process is called as hydrostatic equilibrium. And I did mention about sun producing different elements, and yes, it does. As fusion continues, hydrogen goes to helium, and once helium is over, and this happens only in bigger stars, helium fuses to form carbon, carbon to oxygen, and so on. So, if we continue this process over a very long time, what do we get? You will get this soon. I did say that a sun contains hydrogen. Hydrogen being an atom and due to the high temperature loses its electron and forms an ion. And we do know that in presence of electric field and the sun rotating, we generate a magnetic field. So when sun's magnetic field is generated and it's distorted, we get a solar flare where huge amounts of radiation is just popped out of the sun. But magnetic force wants it back. So it turns back and again comes back to the sun, forming a sunspot. Sunspots, the temperature also goes down. And so does the material. We did speak of the sun burning and achieving a stable state. But what happens once it's about to die or losing out its fuel? A planetary nebula. The sun, when it loses out of helium, now this depends on the size of a star. A smaller star will lose its outer layer of helium and hydrogen because it is not able to balance the force that I mentioned earlier, gravity and fusion. So, what happens to the hydrogen and helium? It is just blown away into the cosmos, which later might result in the formation of planets or other suns. I did tell you we'll be back to what is formed. Hydrogen and helium, the two elements, are formed during the Big Bang. But there are other elements are produced by the stars, such as the ones marked in the yellow are produced by smaller stars like our sun, which produce carbon, nitrogen, oxygen, so on. That's all. And their life ends with a white dwarf. But bigger stars are able to fuse so much and they have so much of energy that they go on fusing, and producing higher elements, which go on. And the pink ones that you see are the cosmic rays, which is a mystery to some extent. And the blue ones are for the stars that are much bigger, who are not able to hold themselves and burst in a supernova. Boom, it goes. A lot of elements are produced in such a process. So, after the sun, aren't we supposed to mention our location? The Milky Way.
we have just seen our complete solar system itself, and also we have just seen about the other solar systems and other planets. But where does this everything lie? It comes into our own parent Milky Way galaxy. Milky Way galaxy is spread across 100,000 light years wide and it is 1,000 light years thick. The center of the Milky Way galaxy contained a giant black hole called the Sagittarius A, and that black hole is surrounded by the bulge. The bulge mostly contains the mixture of old and new stars. And when we just go a little bit across, we find the spiral disk. The spiral disk is something where all the solar systems, all different stars, all different planets. It could be young planets, old stars, young stars. Everything just lie up, and these spiral disks revolve around the black hole. The outermost part of the Milky Way galaxy is called the halo, where when the star gets older enough or they lose the gravitational attraction, they just ping out from the galaxy itself. But where is our address? Where does our solar system comes? Well, our solar system lies around 28,000 light years away from the center of the Milky Way galaxy. Our Milky Way galaxy is one of the kind of many other galaxies in this universe, and our Milky Way is a spiral binded galaxy, but it is not the only one. There are many different galaxies, such as barred, irregular, elliptical, perpendicular, and elliptical galaxies. These galaxies are has their own shapes, own properties, but one common thing is like each and every galaxy has a black hole at its center. One of the spectacular image taken by the Hubble Space Probe representing many different galaxies in this. But there is one incident which is going to take place 1.5 billion years from now, and that's the collision of Andromeda and Milky Way galaxy. This is going to be the beautiful view from the Earth when this incident could be take up place. But luckily, none of us will be available at that time. So no worries, we can still imagine how this is going to take place. But when the universe itself was formed, the galaxy didn't start it there and then and there itself. It was a slow process where the stars were born, they were getting older, and they were forming up into a giant black holes. And that black hole attractions was so high, the gravitational attraction was so powerful that it just managed or merged all the stars into it and formed a galaxy. You can also say the galaxy is a colony of stars. It's little, it's like you can just mention how these galaxies are being formed. But there is one more thing. Sometimes when you just look into some videos or pictures, you can see a jet, a beam of heavy light is coming out from the center itself. Well, that is called the magnetic jet. When the magnetation attraction of the black hole exceeds its own limit, it spread out in the form of jet. It is where when the complete stardust and other molecules are thrown away from the galaxies, and this jet is spread across light years. Our galaxies and many other galaxies are the part of our observable universe. And how do we observe our universe? Well, we don't have a exact evidence of our own universe itself. But through the computer simulation, it was made to be in the form of a brain cell. You can see in the image that the simulated universe is compared with a brain cell. And that's how the observable universe looks like. Observable universe is across 13.4 billion years old, which means it is still expanding and going wider and wider. But where are we? Where do we lie in that giant universe? We are a part of a tiny planet called Earth, which is revolving around the parent star called Sun, and it is a part. And this solar system is a part of many other solar systems which have their own planets and stars revolving in this Milky Way galaxy, which is a spiral galaxy. Which this Milky Way galaxy is one among the trillions and trillions of other galaxies, and this group of galaxies form a cluster called a Virgo cluster, and this Virgo cluster is a part of many other clusters called the Virgo superclusters, and these all superclusters just combine together to form our own observable universe. This was something about the universe, about the Milky Way, about solar system, about the planets, etc. But how this universe actually formed? Well, it was formed to a Big Bang splash, just a bursting of one particular single point and emitting all the gases and molecules, subatomic particles into deep space, and the explosion is just going on. Right now, we have just looked to the maximum scale, to a maximum limit. We have seen everything which is massive in science. But there is something which is called the building block of this entire universe. That's the matter and the antimatters and other subatomic particles. Now you might be wondering what are these strange words, strange stuffs. You are going to just check it out very soon.
That and can manipulate with it. But there are many more mysteries. The unanswered, demystified. As per the most accepted theory, the universe began with a big bang. Boom! And all that energy spread across. But remember Einstein's famous equation E equals mc square. So that says energy and mass are related. So what happened? The energy that was created during Big Bang was equally divided into matter and antimatter. The image that you see now on the screen is the first image taken of antimatter. The one on the bottom being the electron and the one on top being positron. And you might wonder when this was conducted, how it was conducted. You could ask these doubts later on. So we do call it antimatter. So there must be some similarities with matter, and there are. They both the particles, the antimatter and matter. I will be mentioning antimatter as Am now onwards. Have the same mass. They have the same spin. So what makes them different? It is their charge. As per all the observations that were made until now, scientists found that antimatter occupies less than 1%, very, very close to 0% of the observable universe. So, put on your thinking caps. What happened to all the antimatter that was generated during Big Bang? Well, theories still argue about this thing, but there is one that says that for every 10 billion antimatter matter pairs, there was one excess of matter, which led to our formation, luckily. Can we produce antimatter with our present technology? Yes, and it is being produced at CERN and Fermilab. And if it is present and it can also be produced, do we use it? Again, a yes. PET scanners are used to image the cancerous cells. And finally, what are X and Y on the graph? You will find out soon.
Well,
Antimatter having opposite charges, and when they come together, they annihilate each other immediately. This is the reverse of Einstein's equation. Mass coming together and giving out energy. So now you see a video where matter and antimatter, a single particle of those collided to form lots of energy. And this energy can be used for destructive purposes. They say every coin has two sides. Very tiny amounts of antimatter can produce huge amount of energy. So this is another periodic table that has elements. This is a table that shows all the particles mankind knows. The first section being the particles that belong to matter. The second one, particles belonging to antimatter. And the third one are the force carriers. But there is something special there. Why is the Higgs particle mentioned separately or highlighted? It's because Higgs boson or the Higgs field itself is responsible for all our masses. It is an omnipresent, meaning it is present everywhere, here, there, and everywhere. So the more you interact with it, more mass you get. And this particular Higgs boson was confirmed its existence in CERN in 2012. The image that you see was when two proper, very high energetic protons were collided to form a Higgs boson, which immediately decayed though. Now observe the peculiarity in this particular video. This video is of a galaxy, that is a bullet cluster, which collided with each other. Notice that something there was a bluish thing. The peculiarity here is that when two galaxies collide, all of their mass, that is the planets, the stars, all must get very hot. That means give out energy. But what we saw was there was something else that held these galaxies together and moved them across without creating any collision. Think what that could be. And this image or this visualization created was observed actually due to gravitational lensing. It is when, due to a heavy mass, example of gravity, that is created by huge galaxies or black holes too, bend the whole space-time around them that even light has to bend and take another path. So you do see the galaxies looking fully curved or getting stretched around the other thing what is in the front of us. So we did see some evidence of there is something, but do we have any other proofs? As per Newton's theory, the planets or any other star that is revolving close to a star or a black hole has to decrease its velocity or the speed around which it goes as it moves away from the center. But in galaxies, that is not observed. As you go away from the center of galaxy, the speed at which the stars revolve increases. This was observed in the 1930s by Fritz Zwicky and called dark matter. So the 25% or the Y that you are thinking of is dark matter. So how well do we know dark matter other than knowing its presence? Turns out we know a good extent.
Well, you have just observed the subatomic particles, the other particles of our own universe. But and now we have come across to the word called dark matter. You might be wondering what is this mysterious dark matter and why it's named such strange. Well, dark matter is a phenomena which is still unknown to many people and many scientists. The evidences of this dark matter is observed in the motion of the galaxies. When, for an example, just look up the let's take up example of our own solar system. When the planet is close to our star, its speed increases to some extent, but when it's away from the star, its speed decreases. That's because of the change in the gravitational attraction. But when it comes to the galaxy point, the stars which are revolving around the black hole, which, as I mentioned, the Sagittarius A, their speed, when compared to the stars which are situated at the edge of the Milky Way galaxy, the speed is comparatively same. And how is that possible? The gravitational pull is same across the spirals, and it's not only applicable here, but it's applicable in every different galaxies. Well, this showed the evidence of dark matter. We have four fundamental forces of our nature: the electromagnetic, strong force, weak force, and the gravity. But But the dark matter has no traces. It is still unknown, and the only evidence we have is the motion. But the dark matter and dark energy have their own theories and calculated mathematically. The other word and other phenomena called the dark energy. This is something responsible for the expansion of universe. The dark energy is an unknown and uncaptured, or we can say unobserved phenomena too, because we don't have any traces. But one evidence is that the expansion of the universe itself is an evidence of the dark energy. Why? Let me tell you. Due to the gravitational attraction, as I mentioned, gravity attracts everything towards itself. Big Bang was also happened due to a small blush, due to a burst at a one singular point. But after some time, it should again undergo a blast, right? Because of the gravity, the speed with which it's expanding, the forces which are responsible for its expansion would somewhere sometime should get weaker, and the dark energy should dominate it, which means that the gravity should dominate it, which means again these all objects should come to a particular point and again undergo a blast. But it's not happening. Its reverse is taking up. Things are getting farther and farther away, and that is because of the dark energy which is dominating and overtaking the gravitational force of attraction itself. These two things, mysterious objects, are still unknown in the universe. Just take even one more example called the Hubble's experiment, where a few dots are drawn on a balloon, and when that balloon is blown with the air, the dot gets separated, or the distance between those dots increases, as you can see in the figure. That's a small example of the expanding universe. There is something which is dominating it, and due to which the universe is expanding continuously. Well, this is what the dark matter and the dark energy actually represented. These are the still unknowns and a strange mystery to us. We have also represented this in the form of graphs and everything. Let's talk. When we say that everything is expanding, what could be the one source which actually estimated the expansion? That was the cosmic microwave background. This is a radio background which is observed in every direction. This microwave background is something responsible for the Big Bang. When the Big Bang was formed, the radiation has spread across the entire space, and these radio signals were just responsible for the Big Bang and also responsible for the expansion of the universe itself. So when the Big Bang was actually started, it was like a young baby, and everything was very hot, very dense, had high temperatures, and very dense matter accumulated in one single particular place. But today, it's something the signals we get is a little weak, and it's getting weaker and weaker because the expansion is still going on. It's still moving on. Even the objects today expand in a much faster rate than ever. And we might be wondering how this is going to end. Well, this is still a mystery. No one knows how it's going to end because there is no collision taking up frequently. Every object is moving away from each other. Now, just look into some interesting facts of our own universe. Each and every particle, each and every object in our universe has its own identity. You have just seen about matter and antimatter, but antimatter has a great dominance because antimatter is not observed. We don't have a trace of an antimatter, but it do have some facts, and these interesting facts could really impress you, just blow up your mind when you just hear to them.
Gold, which is the most precious metal that we consider and many are jealous of it, is considered very, very important. But antimatter, the cost of single particle 1 gram of antimatter is $62.5 trillion. Imagine if you get a hold of one antimatter particle. Next, the usage of antimatter 17 grams, that is the size of a thyroid gland, that much is more than enough to power a spaceship. And then the fact that amused me too, bananas emit antimatter every 75 minutes. Isn't that amazing? So now we are nearing the end of the session. We have a few activities for you. The ones being
Yeah.
quiz and quizzes.
So you have just seen about everything, whatever we taught today, and we are gonna just put up questions for you, a short quiz. So everybody just fingers on your keys and get ready to answer them. So here we come up with the first question. What are the first astronomical object observed ever by an individual? Just type the answer fast. We have 10 seconds to go. The options would be Mars and Venus, Sun, Moon, Sun, Mars, or the asteroids. Come on, just start it and start answering. Just think of it. What are the two astronomical objects which you can see with your own eyes? Time up. It's the sun and the moon. These are the two things which you can observe anywhere, anytime. Come to the second question. How far is our solar system located from the center of our galaxy? Yes. The options are 28,000, 100,000, 32,000, and 1200. Come on, you have to answer this because it's very easy and it's been also represented in the picture also. Time's up. The answer is 28,000 light years. This our solar system is located 28,000 light years away from the center of the Milky Way galaxy. Isn't it crazy? 28,000 light years. It's a very large distance, and that's why we couldn't see the effect of the black hole Sagittarius A, which is located at the center of the Milky Way, on our solar system. We cannot see the effects of it. But somewhere we do find the traces. Move on to the next question. What is the ratio of antimatter to that of an ordinary matter? Options are 0 is to 1, 1 is to 0, 10 is to 1, and 1 is to 10. We concentrate on the question ratio of antimatter to that of ordinary matter. Here the antimatter comes first. We have just explained, Vishesh has just stressed out, like for every 10 billion antimatter, there is 10 billion and 1 matter. I've just given you a hint. For every 10 billion antimatter, there is 10 billion and 1 matter. Time's up. The answer is 0 is to 1, because when the 10 billion antimatter and 10 billion and 1 matter collide, they burst out in a spectacular glow. A huge amount of energy is emitted, which leads to the 0 antimatter and 1 matter left on. And that's why the ratio is 0 is to 1. Moving on to the final question. What are the two mysterious phenomena of the existing universe? Come on, guys, you have to answer. This was just told a minute ago, a seconds ago. You have to answer this. Options are matter and antimatter, asteroids and meteors, dark matter, dark energy, or the stars and galaxies. The two phenomena, strange phenomena. Come on, guys, you have to hurry up. This is the very easiest one. It was just told a seconds ago. Unfortunately, time's up. The answer is dark matter and dark energy. These are the mysterious things which are still unknown to the astronomers, and the discovery is still going on. What all we know about these two phenomena are written in theories and equations itself, but in the realistic world, we have no traces of it. So with this, we will end up our session, and it was a lovely session with you all interacting, putting up the questions. Before that, we would like to also give you some assignments. In the assignment option, given two assignments. One is about write 50 to 60 words about any star or galaxy, which is your favorite one, and the other one, write something about dark energy and dark matter. You have an option. It's not compulsory, like you have to observe. You have to write both assignments. It's a choice. You can write any one assignment and submit it. It's your guide. It's your choice. And one more thing I would like to request all of you is you have to do one activity for yourself, and this want to be the interesting activity. As I mentioned, that moon has different phases, and that phases takes almost 29 and a half days to take up one complete phase. So what is your activity is right now that you guys are gonna take the pictures of the moon every day for 30 days, and on the 30th day just combine all the images and see, and you can observe eyes that the phases, the transition which is taking up in the phases of the moon, it's really amazing. It will just blow up your mind. And one final format, when you guys will submit your assignments, make sure you have written your name, your student ID, the session name, and the date of submission also. Okay. But as few people over here are 12th graduating, 12th pass out, and or else who are currently pursuing their 12th standard degree or the 10th standard degree, we have some career advices to you. To be if you want to be the person who actually tries to understand the future, understand the universe, who actually who studies about the stars, black holes, and the complete entire mystery of this universe, we have a career guidance to you also. You have to complete your 10+2, which is the schooling till standard in science, and then you have to take up your bachelor's in science degree either in maths, physics, chemistry, or relevant subjects. Then you can, if you are not into BSc, or which we call Bachelor of Science, you can also take your BE or BTech, which is called Bachelor of Engineering and or Bachelor of Technology in aerospace or any other relevant subjects. After that, you have to study Masters in Science. Either the Masters could be in physics, maths, chemistry, astronomy, astrophysics, and there are many other subjects too. And in the last, you have to do your PhD. Okay, you have to do your PhD in astronomy or astrophysics. The job opportunities you have in various space organizations and space researchers.
I do know that this fact was a little hard to take in, but astronomy and astrophysics is a very wide field. So, any more doubts of yours, please do contact us. Only for doubts, not for assignments. Email IDs are mentioned. And again, thank you.
One last time, we thank you all for being a part of this session, and we wish you all a safe stay home and be safe, be secure, and keep learning. And see you in the tomorrow session. Bye bye.